Bismillahirrahmanirrahim. Assalamu alaikum, dear students. Today we will discuss about electromechanical system. Basically, electromechanical system is the combination of electrical and mechanical system. Usually, it has the electrical input and the output is in the form of mechanical. The example of electromechanical system is your antenna azimuth position control system, which you have studied in the chapter number 1, in which the input was the electrical and the output was mechanical, in which the direction of antenna was controlled by a motor, and we give input to the motor in the form of electrical input, and the output was the rotation of the antenna, so the output was in the form mechanical. Another example of electromechanical system is the remote control, in which we have electrical input and the output is the mechanical. Computer tape is also the example of electromechanical system. Disk drive position control system is also the example of electromechanical system, in which you give the electrical input and you get the mechanical output. Now we'll study the electromechanical system. Here we will study the armature controlled DC motor. Actually, from this diagram, as you can see, this is your electrical part, and or you can say this is the circuit of your armature controls DC motor, and here there's a shaft which is rotating, or you can say you are getting the output from a mechanical output. Actually, as you know, that motor is electromechanical component that yields a displacement or output for a voltage input. Mechanical output is generated by the electrical input. Here we are giving the electrical input, and here we are getting the mechanical output. Here it's a stationary permanent magnet or electromagnet. Okay, as you know that when armature passes through the fixed field and feels a force, or you can say that a moving current moving through a magnetic field induce a force. And what is the value of that, the force? For the value of that force is F is equal to ILB. What is I? I is the current through the armature, and L is the length of the conductor, and B is the magnetic field density. And here is the VB. What is the VB? VB is the back electromagnetic force. Okay, the rotating conductor in the presence of magnetic field generate an induced voltage. The value of this electromagnetic force or induced electromagnetic back electromotive force is equal to VB is equal to VLB. And what is the V? V is the velocity of the conductor, and L is the length of the conductor, and B is the magnetic field density. The VB is equal to VLB. Okay, as you know that we have written here VAB is equal to, or back electromotive force is equal to VLB, and you know that the current carrying armature is rotating in a magnetic field. Its voltage is proportional to the speed. So we can write VB. VB is proportional to the speed or angular displacement, right, by Faraday's law of this is VB back EMF or back electromagnetic force is equal to the is directly proportional to the speed. So what is the speed? Speed of this shaft, d theta by dt, and kb. What is the kb? Kb is the constant of proportionality, and it is called the back EMF constant. Okay, or you can derive it from the previous equation. From this equation, V is equal to VLB. Here we put V is equal to R omega, and omega is equal to d theta by dt. So all other constant. R is radius is the constant, length is the constant, and B is the fixed magnetic field. It's also the constant. So we replace these constants, length and B magnetic field, with the constant Kb. Or you can directly write this equation by considering the fact that voltage is proportional to the speed, and by putting this kb as a constant. Okay, what will be the speed of what will be the value of torque acting here? The torque, as you know, by Lorentz law, the force, magnetic field on the force is equal to I into B, means value of current and B the value of magnetic field. As B magnetic field is constant, so we can say that the torque is directly proportional to the armature current, or T is equal to KT. KT is the constant of proportionality called motor torque constant, right? KT, torque is equal to KT into IA, and IA, what will be the value of this armature current IA? That will be equal to the torque by KT, or you can derive it from this relation as well. Tau is equal to FR, लेकिन हमें पता है, but F is equal to ILB. We have written here the force on the armature or a conductor in a fixed field is equal to ILB, and we put the value of F in this equation, R, I, L, B, and all these are constant. R is constant, and the length of conductor is constant, magnetic field is constant. So we replaced all these constant with the KT, and then we left with the IA. So we can derive it from this equation as well, or we can write it directly that the torque is directly proportional to the armature current. Right now we have derived two equations, one for the back EMF, back electromotive force, and other for the torque. Actually, what we have to find, we have to find the angular displacement by EA, means what we have applied the voltage and what angular displacement or displacement we get from this, means this is the electrical input and we get the mechanical output. So we have to find the relation between the output to the input. Output is the mechanical and input is the electrical. Okay, now we will simply apply the loop in this circuit, starting from here, that voltage rise is equal to the voltage drop. And what is the voltage rise in this circuit? The applied voltage is the voltage rise, and where is the voltage drop across this? Basically this is the armature resistance and this is the armature inductance. The value of armature inductance is very low, or you can say the armature self inductance is very low, so we can ignore this. Okay, here we apply the loop equation on this circuit. Voltage rise EA is equal to voltage drop, and where is the voltage drop? We can write IARA plus IA by putting writing the equation in S domain, it will become SLA plus VB, the electromotive force. Okay, we will take IA, armature current, as a common, and rest will be these two terms plus VB or equal to RA. But as we have derived in the previous slide, that RA, IA, armature current, is equal to T by KT, torque divided by constant of proportionality for the motor torque. Okay, and what is the value of VB? We have also derived the value of VB in the previous slide. We will put the value of armature current and VB back EMF in the this equation, and we will get this equation. The value of IA is equal to K by T by KT, RA plus SLA plus the value of VB is KB as theta. We have to find torque in terms of theta. Actually, we have to find the relation between the theta and EA. So we will replace the terms of torque with the theta, and we will find the output. Okay. The mechanical load on the DC motor. What is the mechanical load on the DC motor? We have seen there is a shaft, or there is a fixed load on this motor. We have considered two types of load, JM and DM. This is the inertial load and this is the damper. So this is the inertial load of the motor, and this is the inertial damper load on the motor, or damping in the motion, damping of the motor. So we write this equation as we have written earlier, that the applied torque is equal to the impedances, sum of impedances into theta, and means the angular displacement. Okay, now finding the transfer function, as we have written this equation in the previous slide. This equation number 1, and the value of torque. Actually, we replace the value of torque in, as we have written here, that we have to find torque in terms of theta. So we try to write the value of torque in terms of theta. So the way we write is that applied torque is equal to the sum of impedances into angular displacement of the shaft, or angular displacement. So we put the value of torque T in this equation, and we will get the equation Jm s square plus ds plus Ra plus Sla plus theta plus Kb as theta. Clear? It's simple. We simply put the value of T. This theta comes from the value of T. Now the both terms are in the terms of theta. We have taken the theta common, and the rest of the terms will be written in the bracket. And what will now we will simply rest is the mathematical equation. We will solve the terms inside the bracket by taking kt below all the terms, and multiplying kt with the terms kb. We will get this equation, and the value of our theta by Ea means the output in terms of angular displacement by the applied voltage is equal to kt by s jm ras plus d ra plus kt kb kt. So it's the relation between the output and the input, as normally we do, that the terms with the higher order of the s, we keep the term without any coefficient. So we divide inertia of the motor and the resistance of the armature. We divide the whole equation by the inertia of the motor and the resistance of the armature, and we will get this relation. And this is our relation of the electromechanical system, in which we can get the mechanical output and the electrical input. So if we have any system in which we have given input in the form of electrical, and get the output in the form of mechanical, we can find the transfer function, or we can find the value by using this equation, in which we should know our armature resistance and the motor in impedances, and the value of constants. One is the torque constant, one is the back EMF constant, and by using this relation we can easily find the output. Okay, now we evaluate mechanical constant. Here is this is the motor, and or you can say this is the armature inertia and armature and damping, and here this is again the gear system. N1 is the number of teeth on this, and the N2 is the number of teeth on the second gear. And here is the load, which is driven by the motor. Now the load, inertia and the damping are reflected back to the armature inertia and damping. Actually, as we read in the last previous couple of lectures, that we have to consider the reflected load. For the reflected load, as we have studied earlier, that we have, when we shift any impedance from input to output or output to input, so we will divide the number of so we will multiply number of teeth on the source destination side by number of teeth on the source side. We will take the square and multiply with the impedance, and then we will shift the impedance. Same we have did here. The Jm equivalent, or you can say the equivalent inertia, will be equal to the Ja inertia of the armature plus JL load inertia. As we have shifted load inertia from load side to the source side or armature side, we multiply it with the number of teeth on the destination. And what is the destination for this load inertia? The destination for this load inertia is the motor side. So the number of teeth on the destination is N1, and number of teeth on the source is N2. Similarly, we shifting sorry, we shifted our inertia from load side to source side. Dm, the equivalent impedance, is equal to the Da armature on the armature side plus DL, and multiply with the number of teeth on the load side by number of teeth on the destination shaft, and number of teeth on the source side by square. So we transfer the impedances. Now we have to find the torque speed equation. Means what torque we got from this electrical input. As so we have to find the relation speed torque equation. As we already applied the loop inside the armature circuit, and the equation in the previous equation, we will ignore LA. What is the LA? LA is the inductance of the armature, which the value of this is very low, so we ignore this, and we will write the rest of equation. IRA plus EB equal to EA. Let me show you the equation. This was the loop equation that we have already written. So we ignore this term. The rest terms are written here. So we will put the value of I, armature current, as we have already derived the value of armature current is T by KT, and we will put the value of VB, and we have already derived the value of VB is equal to KB into d theta by dt, and we can replace d theta by dt by omega. Now we put these values in this equation. We will get this given equation, and from this given equation we can easily find the value of torque. Okay, this is the torque speed equation. Now we have to evaluate the torque speed curve. On the x-axis we have written the we have taken the angular speed, and here is the torque. Okay, the relation speed torque speed equation we have already derived. It's written here. Okay, now here the torque will be maximum, but in this case the omega or angular speed will be 0, and when the angular speed is 0, this will be the T stall. What is the T stall? T stall is the when there is such a heavy load or such a maximum load on the motor that motor stop rotating. This is the T stall. Means torque is omega is 0, and the T stall is the torque when motor stop rotating, and omega no load means there is no load on the motor. When we put these values in this equation, in case of T stall, when we will put when the value of omega is 0, omega no load, then this term will become 0. This term omega, we put omega is equal to 0, this term will become 0, and the torque will become T stall. This point in the graph, this is the T stall, and the T stall will be equal to KT by RA into this term. Only this term will left. Okay, now what is the case when torque is 0? When torque is 0, then omega is equal to omega, we can say no load. Omega no load equal to means here omega is omega no load, then we will put torque here is 0. uh, 0 is equal to this term, right? And we will get EA by KB, right? Simple. We have taken KT by RA common. We have taken KT. We will put torque is equal to 0. 0 is equal to these two terms. Then we will take KT by RA common from these two terms, right? These two terms will multiply with 0 and will become 0. The rest will come KB omega m plus EA. And omega will become EA by KB. Simple. Clear these both equation. T stall, I will repeat again. T stall we get by putting omega 0 in this equation, and omega no load we get by putting T is equal to 0 in this equation. These are two equations we get from the torque speed relation. Now, basically there are two important relations in electromechanical system. One is the this transfer function, other is the constants KT and KB. The value of KT and KB can be found from this T stall and omega no load equation. Now here is our an example, and this is the example from your book. I think example number 2.23 of your book. Here is the electromechanical system in which there is a load. Motor is driving a load, and the value of JA in armature inertia and load inertia, and armature and load damper is also mentioned. Okay, and this is the graph we have drawn here, in which EA is the input voltage, the 500 is the value of torque T stall, and 50 is the value of omega no load. We have to find the output by input. The relation between the theta by EA is equal to this. Now first we have, as you know, the value of all, we will put the value of all the terms, and we will get the relation between these two, theta by E. By inspecting this equation, we can see that the value of RA, armature resistance, is known. The value of DM, the value of DM. So first we have to find the value of equivalent value of means we have to reflect our inertia and viscous damper from load side to the motor side. We will use the same equation as we have studied earlier. Jm is equal to Ja, the inertia of the armature, plus load inertia divided by the multiplied by the same ratio of the gear ratio, and the equivalent viscous damping will be equal to the damping of the armature plus damping of the load multiplied by the gear ratio, teeth ratio. So in this relation, we are familiar with the DM, JM, RA. The two terms which are unknown is the KB and KT, and the KB and KT we will find, as I have told you earlier, from these two equation, T stall and omega no load. Okay, from this graph, as you can say, T stall is equal to 500. So the relation was T stall equal to KT by RA into EA. So 500 will be and the value of EA input voltage, EA is equal to 100. So 500 by 100 is equal to kt by Ri, and the next unknown was the value of kb, and value of kb can be find by the omega no load equation, and omega no load is equal to 50 over kb, ea by kb, and input voltage is 100 by kb, and the value of kb is 2. So the value of kt by Ra is equal to 5, and the value of omega no load is equal to 2. Now we will put all the values. The value of kt, value of kt by Ra, the value of kt by Ra we have is 5. kt by R is equal to 5, Jm is equal to 12, S plus dm, value of dm, and kt by, again the value of kt by R is Jm. Simply by putting this value we will get this equation, and by simplifying or by multiplying this equation we will get the relation between theta by Ea. So we have completed our chapter number 2. Hopefully you have cleared all the transfer function: electrical transfer system, mechanical system, rotational mechanical system, gear system, electromechanical system. From the next lecture we will start the chapter number 3 of your book. So if you feel any difficulty, we will discuss in comment section, or we can discuss in our upcoming online class. Thank you. Inshallah, see you in the next lecture. Allah Hafiz.